Okay, you're live now.
Okay.
Please go ahead.
Okay. So as I said before, now I'm going to present a new type of application. It's a bit different from before, but it uses the same basic fundamental processes of instability, but applied to the nearshore region and to the case of surface gravity waves in particular, and how they affect the circulation. This is something I'm doing for a few years now, and I think it's interesting application of non-hydrostatic dynamics. As an introduction to nearshore circulation and surfzone eddies, we can first realize that rip currents, which it's the main form of eddy circulation in the surf zone, they are responsible every year of a lot of damages, a lot of people dying. And actually, this is the result given by the US, and they show that they have more dead people by recurrence than by any other problems in their country, including sharks, of course, which is very small, hurricane and tornadoes. So it's a problem worth studying by oceanographers, and there are actually a few people doing that. So what is the problem with rip currents? The thing is, we don't know that much about it. It's quite difficult to observe with instruments because surf zone is, as you may understand, very problematic for instruments, very dynamic, very energetic. And so as you see on this picture, there are all kinds of scales involved in the dynamics. Some large plumes, which are the main ribs, but then also some smaller rib structures, and then even smaller scales that you see on the foam. So this is the challenge that is proposed to modelers, especially with 3D models. We started to study rip currents, particularly channeled rip currents, the currents that are produced by a channel in the topography, with wave average modeling. As I mentioned before, CROCO has wave average equations, that is, equations with extra terms that accounts for the effect of waves. In the case of the nearshore circulation, the important extra term is the one that transfer momentum from the wave to the currents when the waves are breaking in a nearshore zone. And we have used these equations in a few instances with good results, but we are limited in the use of these equations by some processes that I will describe. The main thing that we can't get is the full spectrum of waves and their effects in the circulation. Because when we use wave average equations, that is waves average over multiple periods, we can only consider long-crested waves, which are shown on the left here. In reality, the waves are not long like this, or rarely. They tend to be short-crested, like in the middle. And this is because of interferences between waves coming from different directions. Even when they come from one direction, there's a spread in the direction that is enough to generate interference and make individual waves short, that is with a finite distance. And this is important. Why? when using two-dimensional models that can resolve waves, when they produce short-crested waves, they can then generate vorticity when they break. Like you see here, the wave is breaking and generating vorticity that materializes as a rip current. And this is a process that you can only produce with a wave resolving model. Therefore, the wave average model is not capable of doing that. And we need to have a model that actually resolve waves. Again, 2D models are very good at generating the what we call flash rips, because they are not rips that are associated with a change in the topography, but they are generated by the short-crested waves. So they are very good at doing that, but they tend to overdo it, to generate too much energy. And up to now, we didn't know why. So the hypothesis that we made is that the 2D model cannot resolve the three-dimensional instabilities and three-dimensional shears that could prevent the that could somehow control the generation of field currents. And so we turn to 3D models, and for the nearshore region, for waves, you have two kinds of 3D models that can resolve waves. One is called the VOF, or volume of fluid model, and that is classified into the LES type of models. And these models can solve the turbulence produced by braking, which we see here as a roller, a vortices, and revortices. So this is nice. These are timescales that are lower than a wave period. They are short timescales, and it's very refined simulation, but it's very expensive, and so we cannot use these models to integrate for a long time. It's only for a few waves, and only in 2-dimension or 2.5 direction, we'll say. So more and more modelers turn towards free surface models, just like CROCO or other models like NH-Wave or SWASH. So these are free surface, non-hydrostatic models, of course, because short surface waves are non-hydrostatic in nature. And then the currents that are generated are also, to some extent, non-hydrostatic. In this case, we cannot produce the turbulence generated by braking. We have to parameterize it, but we can produce the waves and the currents generated by this turbulence and the instabilities that are generated by these currents. The time scale of instabilities in this case is larger than a wave period. And the instabilities are of the type of Kelvin-Helmholtz also, shear instabilities. So we started to work with CROCO on generating waves. And the first thing to do is to make sure that the waves that are generated are physically sound. So the best way to do that is, again, to compare with laboratory experiments. And that was one of the experiment that we used, called the Globex. It was made at in the Netherlands, in a laboratory, and we try to reproduce exactly the conditions of the experiments by generating waves at the offshore boundary, and then the particularity of this experiment is that we had a very high resolution of observation of the surface waves and of the undertow, that is the currents that is at the bottom of the beach. And the comparison with data that you see on the right was very good in terms of all the moments of sea level and undertow. So we were particularly happy with this. And then there was another test. This one is a full-scale plume experiment, also in the Netherlands, with actual real waves and a real scale of a beach, and a full spectrum of waves. So we use that also to generate waves at the offshore boundary. And this time we compare the profile of currents that you see in the middle to see if they will match the observation. And the profile of currents, the vertical profile of currents, is very important because this is the profile. If the shear is enough, and it is, it can generate vertical instabilities, vertical shear instabilities. So this validation was particularly important. So the next step is going towards a full 3-dimension. And in this case, we compared with some observational experiment that was performed in Grand Popo Beach in Benin, that is in the Gulf of Guinea in Africa. Waves are coming with an angle, and they produce then currents that are cross-shore and along-shore. Here I have an animation to show you the generation of waves by the model. So as you can see, these waves are short-crested. That is, they are not uniform on their lengths. They have a limited length scale, and they break at some places before reaching the coast. The white patches are the model produced by the model of turbulence, and they show the turbulent energy due to breaking. And you see also some reflection of waves that are going back offshore. And the wetting and drying scheme of the model also seems to work quite well because it produces the swash zone with a realistic ventilation. And then we can look at the currents, the mean currents, the currents that are averaged over multiple periods of waves. We have done 2 experiments that I can show here. One is what we call shallow breaking, which is the full 3D model equations. And for comparison with the 2D approach, we developed an approach in which we have something that looks like 2D, and we call that pseudo 2D. In this case, mixing in the vertical is increased so that the profile of currents that I've showed before is reduced to nothing, and therefore we are very close to what a 2D model will produce, but we can compare it directly with the 3D model. So in this case, with the pseudo 2D model, we tend to reproduce what the usual 2D models do. That is the generation of 2-dimensional filaments and eddies. Very strong flash rips that we see here evolving. They are advected by the longshore currents here to the south, to the bottom of the page. And they are quite classical results. But then we'll show the animation of the full 3D model, and it is quite different. That is, we see more or less the large-scale eddies produced by the 2D model, but on top of that, we have a rip structure that is added to the 2D dynamics, and also the flash rips are not as strong in this case. They are not as large and as strong. So this is just an image showing the same thing with more details because it is higher resolution, this one. And we could compare with some observation, some drone observation of the sediment suspended in the surf zone, also with the foam. And in the middle, it is a model in which we included a sediment transport, resuspension and transport. And the foam is just the convergence and divergence of the currents. And on the right, it's the same result for the pseudo 2D model. And you can see that the 3D model produces a picture that is much more realistic compared to the images, which means that the strong filaments that are produced by the 2D model, the strong ribs, are probably too strong. And what is missing is this rib structure that are smaller eddies that are truly three-dimensional. And that can be illustrated again by a spectrum of energy, where we see that the 2D model does indeed produce less energy for the large eddies, while they produce more energy for smaller eddies. Okay, so this is just that was just an introduction to the problems that are posed by nearshore dynamics and rip currents. I wanted to illustrate quickly something that is on the other side of the spectrum in terms of scales, because it can be interesting. It is an aspect of non-hydrostatic equations that we have not presented before. And it is generally called quasi-hydrostatic equations rather than non-hydrostatic, for the reasons that are following. Here, okay, we talk about large scales, equatorial waves, and the equations are represented on the left. They look like the usual hydrostatic equations, but the terms in red are the additional Coriolis force components, the additional components of the Coriolis force that are generally neglected because they're considered small. But at the equator or around the equator, they are actually not so small, and they need to be included. The reason why we call that quasi-hydrostatic is that because there is a term that enters the hydrostatic equation, the last one, and that changes the hydrostatic balance. So, as an illustration, we compared. It was done by Bertrand Delorme at Stanford. Compared the MIT GCM model in hydrostatic and quasi-hydrostatic mode and CROCO. In both cases, the hydrostatic mode is not able to reproduce the rate of propagation of waves the same way you get it in the quasi-hydrostatic case. It is much more pronounced here in the quasi-hydrostatic case. It's true for MIT GCM and for the CROCO model. The difference between the two models is the MIT GCM is a Z model rather than a sigma model. And you can see that there are topographies that are locking the rays of waves, and they produce some noise in the Z model because of the step-like feature of the topography. While in the sigma model, the noise is removed, both for the hydrostatic case and the non-hydrostatic case. And also, the energy of the waves in CROCO are stronger, and this is probably associated with the numerical aspects of the model. So this is an illustration that non-hydrostaticity can reach all the scales of the spectrum, and also it's introduction to the problem that I will talk about after. It's a numerical aspect of the treatment of these equations. So this is the final chapter of my presentation. Okay, so numerical methods. I will make here a brief introduction. I don't know how much you have been familiar with numerical methods in models, maybe not much yet, but okay, I will start with this. This is a general presentation of how works a numerical scheme. On top left, you have the initial condition, which is a Gaussian function. And this Gaussian function is advected by a constant current. And we observe the working of different kinds of advection schemes. The simplest one is the centered advection scheme of second order. In this case, we use only points that are around the cell, the grid cell where the advection takes place. And the error of this advection scheme grows with the grid space delta x squared, and it is proportional to a third order derivative. You remember that we said that before, a third order derivative means dispersion, wave dispersion. So these center schemes, like all center schemes, are dispersive. That is, the leading order of the error is dispersive. And the dispersion is very clear here, where you see the Gaussian that is being dispersed into waves that are quite large, actually. And they are destroying the initial shape. Then you can go higher in the order of the scheme by using more points around the center cell. So you increase the size of the stencil of your points, and you can get, for example, a fourth order scheme, which, so as a fourth order, is proportional to the fourth power of delta x, and it is also proportional to the fifth order of derivative, which means that is still dispersive. But you see that the dispersion is a bit lower in this case. And of course, the spectral method, which is shown on the bottom right, will be a much better method, but you cannot use it with realistic applications, particularly with respect to boundary conditions. So we want to use higher order methods, but we need to have some diffusion that can control the dispersion part of the advection term. And this is generally done using upstream schemes. In an upstream scheme, the stencil is biased upstream of the cell. And the result of that is that the leading error of the scheme is not proportional to an odd order of derivative, but to an even order. So the first order upstream scheme UP1 looks like a Laplacian diffusion operator with a second order derivative, and is proportional to delta x. So that's why it's first order in terms of accuracy. And in this case, you see that the Gaussian is smooth considerably. And that's the reason why nobody uses this kind of scheme, even though it has very nice properties of monotonicity and stability, etc. But it is very diffusive. So we can go up in order again, and you see that the Gaussian is, in this case, very well reproduced. It is we have an error term, a leading error term that is looking like a hyperdiffusion, a biharmonic diffusion. That is a fourth order derivative. And we can show that all upwind schemes of this kind always have an optimal damping of the dispersion error, so that we have, with this kind of schemes, some kind of optimal schemes. And this is the default choice in CROCO for this reason. Okay. Recently, we updated from the UP3 schemes to UP5 because in some applications we could show that using even higher order of advection scheme, going to UP5 means using an hyperdiffusion of order 6. And in this case, using UP5 compared to UP3 is equivalent to doubling the resolution of UP3. So if you double the resolution of UP3, your cost is about double also. While if you use a UP5, you have basically the same result, but at a cost that is only 6% of the initial cost. So it is very interesting to go up in order of the advection scheme. So UP5 is becoming more and more our default choice in the simulations. So talking about non-hydrostatic simulations, how does it apply to the very small scales, what I just said? So what I said is fine for mesoscale and some mesoscales. Can we apply all this for the non-hydrostatic case? So in this example, it appears that it is very advantageous for the internal solitons, because on top you have a solution with higher order schemes in CROCO, and you see the soliton that is surrounded by a red circle, which already shows a trend of soliton, considering that we have 200 meter resolution, which is very marginal in terms of resolution for this kind of processes and dynamics. For example, the model below with a low order scheme shows a soliton that is almost not visible. It is very smooth. So even when we go at smaller scale, high order schemes are still very advantageous. But there is a but. We have to mention another aspect of an advection scheme that we didn't see before. And this aspect shows very clearly when we approach shocks, that is sharp fronts where a problem can occur. So with the Gaussian, UP3 and UP5 are perfect, and we see that again on the central panel. But when we use a step case function, which is basically a shock, then you can see that UP5 develops strong oscillations right at the shock. And this is well known by turbulence people. They call that viscous shocks, and that can generate hyperviscous vortices. You don't see that with UP1, you notice, because the Laplacian operator is truly monotonic and prevents any oscillation. But when you take a higher order even derivative, I said before that an even order derivative is a damping function. It tends to damp things, but it is not totally, it doesn't exclude totally any dispersion. Only the second order derivative is not dispersive at all, but the sixth order is has some kind of dispersion there are some terms that are dispersive in there. And the only way to correct that is to use corrections at near shocks. And some advection schemes do that, like the Weno 5 advection scheme that is in CROCO now. And you can see that the UP5 is completely corrected for shocks at the staircase function. So this Weno 5 is becoming also our default option for non-hydrostatic simulations or very small scale simulations. An illustration of why it is important in realistic applications is again with the internal soliton problem at Gibraltar. When using usual non-monotonic schemes on horizontal and vertical, we are generating oscillations that are visible here above the topographic features. And these oscillations at a certain point were making the model blow up. So we had to find a solution, and that's why we started to develop monotonic schemes with energy. And here it's not WINO but TVD, which is also a monotonic scheme, and the oscillation disappear in this case, and the model doesn't blow up, and we can run it for as long as we want. Another illustration of how the hyperdiffusion problem works. I have 3 cases on the Kelvin-Helmholtz instability problem. On the top left, we use a centered scheme for the vertical advection. So you remember that the center scheme is dispersive. And in this case, we see that the Kelvin-Helmholtz instability produces waves of dispersion and also additional instabilities that we did not expect at this resolution. When we correct the center scheme using a spline, what we call a spline scheme, which is a compact scheme force order, which is much less dispersive, in this case, we still have some amount of dispersion, which is due to the hyperviscous shocks that I mentioned before. And then when we use the WENO 5 scheme below at the bottom, all this numerical dispersion or artificial dispersion is gone, and we only see instabilities that are due to the physics. And so that's actually a nice illustration of why these schemes has become our standard scheme for small-scale applications. Okay, the last part of this section on numerical aspects is the turbulence closure, because we tend to think that we need to model sub-grid scale turbulence, the turbulence that we don't solve. We need to model the flux of energy that goes to the sub-grid scale. But this cannot be done independently of the numerical schemes that we choose. And I will show an illustration of why, but for LES or RAN simulations for 3D instabilities, we now have 2 choices. One is GLS, that is a large range of 2.5 closure models, K epsilon and K omega in particular, which are very much used in the community. And then we have also a choice of 3D Smogensky turbulence model. Usually the Smogensky model is used for LES, for the LES approach, because in the LES approach, the length scale of turbulence should decrease with the resolution, and that's what it is in Smogensky. While when you are in the RANS approach, you don't fully resolve the large eddies, and in this case, you need a model that has a length scale that represents the large eddies. Okay, it's a bit complicated in terms of physics, but usually the separation between these 2 types of turbulence model is done that way. And then again, you have to try one or the other in each application in order to see for yourself, maybe. But in many applications, I would say that the K epsilon or K omega models are working very well. To illustrate the fact that you cannot simply think of turbulence model without thinking of numerical closure, that is the numerical damping by your schemes is the following. Here I put the viscosity that a Smogonski model will give you in terms of a length scale and a velocity, a turbulent velocity scale. The coefficient that is before it, I call CS, is of order 0.01. And then using an upwind scheme, for example, you have a similar scaling that is Cn times L times U. In this case, Cn depends on the scheme. For UP3, it's 1/12, and for UP5, it's 1/16. So you see that even with UP5, you tend to have a coefficient in front of these dimensions that is too high. This means that if you're not careful with the schemes that you use, you will tend to have your dissipation in a model dominated by numerical schemes rather than your physical turbulence closure. So it's a consideration that we need to have in general in modeling. As an illustration below, you have the soliton using Win of 5, and then the same soliton using a centered scheme with diffusion to counteract the dispersion waves. And you see that the solution is not at all the same, and it can even be worse with instabilities. So the conclusions of my presentation, that's the general conclusions. So CROCO is designed for bridging gaps. It's more and more obvious. I think it will be the mark of this model. So we go from quasi-geostrophic ADs to microturbulence now. And we go from oceanic problems to the nearshore zones. So we have two approaches. One is a very original approach, that is the compressible or non-Boussinesq approach, and it has many advantages: accuracy, performance, especially with polarization, versatility. I've shown multiple tests and applications that validate the good performances of the model, and they help to further develop this model. Of course, there is room for improving, in particular the numerical methods and the parametrizations. So we want to go towards even higher order monotonic advection schemes, improve the boundary conditions, especially when we want to introduce porous media like mangroves or maybe protection structures that are porous. And we want to go towards multi-resolution. I will stop here.
Thank you, Patrick. Thank you very much.
Okay, stop sharing.
Question here from David: if you want to use a non-hydrostatic capability, does it make sense to couple the model with wave-watch tree?
Yes, we can use the non-hydrostatic capability with wave-watch 3. In this case, you don't use the non-hydrostatic equation to produce waves, because the waves will be given by wave-watch. So you will use the wave average equations. But then the currents that will be produced by the wave average equations will be non-hydrostatic. So yes, you can do that. So you will not do that to generate waves, but to generate currents forced by wave-watch 3. And these currents will be non-hydrostatic. It's a different kind of application, if you want. Compared to what I've shown, it's a different kind of application. For example, you can, when we did the Langmuir circulation, in this case, it was not, I helped doing it, but it was done by this group in Poland. They didn't use wave watch, but they used analytical waves to produce stock drift, and the stock drift interacting with current will produce the Langmuir cells. You could use WaveWatch to do the same. So in this case, you don't use non-hydrostatic equations to generate waves, but to generate the Langmuir cells, which is different. It's
Okay. Anyone else? Questions?
I see one question about the rib structures.
Oh, yes, yes.
Okay. How do we identify rib structures? Using vorticity or the Q vector, which is another diagnostic to identify any structures. It's the usual diagnostic that turbulence people are using to diagnose current structures, basically.
I was asking because my my understanding was that these ribs are like very fast currents, if I'm correct.
Yes.
So, okay. So I was wondering whether you actually within a region, you look at regions of maybe high velocity compared to the neighboring regions and identify a rib current or something.
Actually,
that was
not. Yes, yeah, okay, I understand. No, they are not particularly high velocity, but they are higher frequency than the usual ribs. So it is like it is true that I understand your question now. So if you have an ADV to observe the currents, you will catch we catch the waves with their periods and frequencies, and then you will catch infragravity waves with a period of about 1-2 minutes. And then you will catch lower frequency ADs of 5-10 minutes. But the rib structure that I showed are mixed with the infragravity waves. So from the instruments, I don't think you can see them. Because, and actually I think that a lot of infragravity waves have been identified wrongly, and maybe they were not infragravity waves, but rib structures. There's no way to differentiate them through if you have only one point of measure. That's a good question. Thank you. Yeah.
Anyone else? If not, I will stop.